In this video, I'm just going to give a walkthrough of the solution to the graph classification exercise. We start here with some text and boilerplate. First, let me talk about this data set. Usually, with the other exercises anyway, we've just used the built-in data set that was given to us by OGB. But here, because of this nuance around DGL and the way they batch together the graphs into this one single graph object, they have a particular opinion about how our data set should work and how our iterations should work. And specifically, the thing that they want is that when you iterate over your data set, they want the first item to be the graph in the mini batch, so one of the graphs, and then the second element that's returned is the label for that particular graph. And what happens when they have instructions here that tell you basically to do this and give some examples. But what happens is when you create a data loader and iterate over it using a data set of this type, then it knows that it can batch together all of the first elements, which are the graphs, into this supergraph object. And when you take a single iteration from the training data loader, for example, this first item that's returned is a single graph where all of the graphs in the mini batch have been combined, and then this tensor that has a label of all of the labels combined into this single tensor. We have a batch of 32 graphs, so we have 32 labels here, and then all 32 of those graphs were combined to create this single graph of, says, 728 nodes. But we know that on average, each graph in our mini batch has something like 20 nodes. And we can see that if we call this dgl.unbatch on this object here, we actually get our original small graphs back. We have a list of our 32 graphs in the mini batch, and we see things like number of nodes equals 24. So this is just showing you how the batching and data loading work with DGL and graph classification tasks. And we also now have this batch that we can play with downstream code. So for example, we call this supergraph object by batch 0, because if we put a 1 here, it would be that label tensor. But if we call 0, we get the actual graph object. And we can look at its data. So if we call the .inData attribute, we see that there's this key feat for feature. And this is the integer encodings of all of the atoms in this batch, all stacked together. And then we also have eData. So this is the features on the edges or the bonds, and that has the feat key as well. We're going to use project each of these things into 300 dimensions, our embedding dimension here. And this is just copying the PyG implementation that's on the leaderboard for the models that we're going to be using. That brings us to the actual GNN layers. So we have the graph isomorphic network layer. The way this typically works, if you look at the paper, to calculate an update to an embedding for a node I, we take its current embedding and we multiply that by 1 plus this small constant that's learnable, this epsilon. So that's going to just give a slight change to the scale of its original vector. And then we're going to sum together the embeddings of all of its neighbors. And once we get this, these two terms added together, we pass that result through an MLP. And that's how Gen usually works. Here, however, we have edge features that we would like to use. And notice that this original equation doesn't have any edge features. These are just node embeddings. To incorporate that, we're going to use the same process that the reference implementation does on the leaderboard, which is instead of just copying the source node embedding as the message, it's going to add the source node embedding to the edge embedding and then pass that result through ArrayLu activation. So this is now the message, and we're going to add all of these messages together, just like before we used the copy of the embedding as the message and added those together, and then finally add it to our current embedding for the node. Now, this introduces a slight complexity because usually with the message passing API of DGL, you specify both a message function and a reduce function, and there's a number of built-in functions. So to do just this one where we're copying the source node embedding, we can use copy U. So U is an indicator of the source node, and V would be the destination node, what we have labeled as I here, the one we're updating, and U is each of the neighbors. So to do this update, we would just say copy and then sum, and that would do this message and aggregation operation. However, there's no built-in function for adding the source node embedding with the edge feature and taking the ReLU activation. There is a built-in function for doing this sum, but it doesn't include the ReLU activation, so we need to handle that separately. And that's essentially the task here. And the way that you can separate this computation is first you calculate the messages without any aggregation. And the way you do that is you call a apply edges method, and that'll create a message along each of the edges. And then you can call update all by saying copy the messages along the edges and apply your aggregation function. So this is how you could do the same equation here, but using the two-step process. First you call copy, and then you separately call update all. So this will create the messages, this will use the messages to aggregate. And that's what we're going to do here. We have, here's the to-do in the class that we're trying to implement here. The first thing we do is we have these features passed in here for the nodes and the edges. And these have already been passed through the atom encoding and bond encoding layers. So these are the actual 300-dimensional embeddings for each. They are not the integers. And these are the things we want to add together. So essentially what we want here is to add each of the source node embeddings to each of the edge embeddings and apply ReLU and add those together. The first thing we'll do is the actual addition, and DGL has a built-in function for adding the embedding of the source node with a feature on the edges. And you have to reference these by the keys that these tensors are stored in. So in here, we stored the edge data into a key called bond, and we stored the node data, the node features, into a key called X. And these are the two things we want to add together. So we have U add E, and the things we want to add is X for the node, the U, and bond for the E, the edge. And then you have to give it a name so that you can pull it back out. And we're going to just call it M for message. Step 2 is applying the ReLU. So we've taken the sum, but again, this does not do ReLU. We need to handle that outside. So we just go ahead and pull M out of the graph, which is created here, and we apply ReLU to it. And we store that back into the graph as M. So we've pulled it out, applied ReLU, and stored it back in. And now we can actually do the sum part. And here we want to say, okay, we've already calculated the messages and we called them M, so just copy them and we'll call them M again, it doesn't matter. And then sum them. And we want to sum the things called M, and we want to store that result in something called MP. And this will be at the node level, and I'm using MP for message passing. And finally, we can extract that out. So we can take the MP key out of the node data and store that as a tensor, which then will be used in the actual update equation here. So we have HMP as representing this sum of the messages. So here we have 1 plus epsilon times the current node embedding, X node, which are the same things that are passed in here. Those are the current node embeddings. So we have 1 plus epsilon times X node plus the result of the message passing, which we took care of here. And that's it. That's the graph convolution for GIN. And I also have a placeholder for the virtual node that we will be able to pass in. As right now it's this optional thing. So if it's none, it's just ignored. But if it's there, it adds in the message from the virtual node. So here we have just a few tests and testing did the number of parameters match. And if you run this, you see that it returns some tensor. And this is the real thing to make sure that the code works. Next, we get to the node level GNN. And we want to essentially stack together those GIN convolution layers. And we're also going to take, this is the class where we'll use the atom encoder and bond encoder to take the integers into 300-dimensional embeddings. And then once we have that, we want to pass it through these convolution layers and then normalize them with batch norm layers. So here I just create these containers, module lists, and then I loop over the number of layers that we have, and then I add a GIN layer to my comms list and a batch norm layer to my batch norms list. And likewise, I loop over those and call .reset parameters on each in this reset parameters method call, because both of these have them built in. Batch norm is built into PyTorch. The GIN layer, we actually defined it above. Now to the forward pass. This is going to look very much like other things we've done in previous exercises. The only difference here, which I actually provided, were these calls to these built-in encoders that OGB provide. So we have the atom encoder, where we're just passing in the integer features, which, as we showed at the very beginning near the data loader, that the node data features are stored by this feat key, as is the edge data. So to get the node integers, we call .indata, and to get the edge integers, we call .edata, and then pass in the name of that tensor. And then those integers are input into the atom encoder to get the node embeddings, and the bond encoder to get the edge embeddings. Now we can loop through the layers that we have and pass in each of our things. So we have the graph that we're going to pass in, we have the node embedding, and we have the edge embedding. And we just implemented the layer that's going to combine all that information. And we store that result in H, which we then pass through the batch norm layer to get a normalized H. And then we say, if it's the last layer, we will do dropout. And if it's not the last layer, we will first do ReLU on H and then apply dropout. In other words, we skip ReLU for the last layer. And then we return H. This should look a lot like previous things because it's a node level GNN embedding task. Here we test that and make sure that a forward pass doesn't have any exceptions. Finally, we get to the graph level GNN. Here we're going to use mean pooling, so we're just going to average together all of the nodes for each graph to be the graph level representation. And here we're going to have to do these readout ops, where we manage or handle this complexity rather about this supergraph combining everything, and now we need to keep track of which node belongs to which graph so that we pool together the right things. Our graph level GNN is going to first of all have the node level GNN as a component. This is going to take our graph. It's what we just implemented, but it's going to take our graph and return embeddings for every single node in our supergraph, and then we need to pool those together so we get graph level representations. So if that batch had something like 700 nodes, then the result of this will be 700 rows long, but that came from 32 graphs, so we need to transform that from 700 something to 32 to get a graph level representation where every row represents a graph, and we'll pass that through an linear layer to get a prediction, and that will be the output of this module. We go ahead and have the reset parameters for each of those, but here's the node level GNN we just implemented, and we can extract the embeddings by just passing in the graph because the integer features are stored as part of that data structure. So now we have H node. These are our node level embeddings, and now we need to apply this readout op, and we said we wanted to take the average. Well, DGL has this built in. The only thing you have to do is assign it a name in the graph so that you can reference it here in this dgl.meanNodes. And so we go ahead and store this in to the node data as H, which is, again, the output from our node level GNN. We store that as H, and then we say, okay, do mean nodes on this batched graph or supergraph, and the thing we want you to take the average of is called H, which we just copied in here. And that is stored into this tensor here, hgraph. So these are the 32 graph level embeddings, which we can then directly pass into our linear layer to get a prediction, which we return. This part's pretty straightforward. This allows us to create our final model and train it. This training took quite a long time. You might see a slightly different answer on the uploaded because I ran this a second time and got slightly different numbers, but the conclusions are the same. It's a little bit higher mean and a little bit higher standard deviation, but looks well aligned with what the leaderboard shows. So I feel pretty good about this. I'm not sure why the variation is higher, but in my case it was. So that's it for the regular baseline gen implementation that incorporates these edge features. Next we go to the virtual nodes. This one got a little tricky because we had to both manage the complexity of this batching situation by making duplicates of the embedding for each of the graphs in the batch, but then also we had to manage the complexity of node level to graph level and this manual message passing because we couldn't treat the virtual nodes in an identical fashion since they didn't have features, they didn't have node and edge features. So there was a few different things going on here that made it a little bit more complicated. Let's go look at the implementation. First, let me point out we have this lookup embedding for the virtual node, and we're going to use these essentially as features. And we want it to match the length of all the other embeddings we're using here, which is this 300 from our encoders. And we're going to use a lookup embedding, but only a single element. So we're going to basically have a table with one row in it, but 300 columns that represent the features of this virtual node. And the way these embedding layers work, if you've never used one, is you pass in integers, where the integer is essentially the row index. And in this case, we only have one row. So the only value you can actually pass into this thing is 0. And when you pass in a 0, it will return this 300-dimensional embedding to you. So in our forward pass, first we, of course, get the embeddings for the atoms and for the bonds using the nodes and edges, integers passing into the atom and bond encoders. But then here we're using this embedding, lookup embedding layer, and we're passing just 0 into it. But we pass in 0 32 times because we need 32 copies of it, one for each of our graphs in the mini batch. So here we pass th zeros, and we use the batch size, which will be 32, and then we pass in all of those zeros to get 32 copies of the same thing, which we now store as H virtual graph because this is at the graph level. So now we have a different copy of the embedding for each graph in our mini batch. Here's where it gets a little trickier. We want to copy each graph's embedding for as many times as it has nodes in that graph. So let's say we had 2 graphs in our mini batch where the first graph only had 2 nodes and the next graph had 3 nodes. then what we would like is something that was an indicator for each node that told it which graph it belonged to. So the 0th graph is the first element because we have 0 indexing. And since there's 2 nodes in that graph, we'll have 2 zeros. And since there is 3 nodes in the next graph, we will have 3 ones. So think of this as an indicator that tells you which graph the node belongs to. And we'll have 5 total nodes because there's 5 nodes in all of these small graphs added together. And the way we're going to use this is, recall that we have a copy of each graph in hvert graph, a copy of the virtual node for each graph. And if we were to pass in, let's say 0, 0, then we would get 2 copies of the first graph's virtual node embedding. And that way we're copying the graph level thing for every node that that graph has. So what we would end up with if we passed in this is 2 copies of the first graph's virtual node embedding and 3 copies of the next node's virtual node embedding that would correspond to these 3 nodes. So this is our way of mapping from the graph level to the node level, because we have this indicator thing that will copy, since these things are duplicated for each graph index. And there's one other layer of trickiness here, because the DGL broadcast nodes seems to need a tensor that has an extra dimension in it, because it's expecting that you're copying a feature from your graph, from each of your graphs to all of the nodes in that graph, but it's expecting a full tensor. And we only have a single item here. So we basically call this A range to be the feature that we're propagating is 0 for the first graph, 1 for the next graph, 2 for the next graph. So we can use A range, which is just 0, 1, 2, 3, all the way up to this batch size. But we need to add this extra dimension on there because we want basically a list with a single element in it for each of the features. So this will look something like 0, 1. So when we call this unsqueeze, it adds in that additional dimension as opposed to just that. And then this will send this feature of 0 to all of the nodes in that first graph, and then it'll send the feature of 1 to all of the nodes in the second graph, which essentially creates this thing. But now we have this additional dimension added to the tensor, so we call squeeze to get rid of it. So we have to add it in just so we can call broadcast nodes, but then we immediately drop it here and turn it back into that type of format. Ignore these numbers here. I'm just talking about the number of brackets that are included. So this is a pretty tricky part here to make it run without exception. But now we can easily convert from the graph level, which is this, to the node level by adding in this duplicated index thing. And now that we have the node level, we essentially have the message that we want to pass for the virtual node. And we pass that in to the forward pass of the convolution here. Because recall, when we implemented that, we had this dummy thing that we set to none and ignored in the forward pass, which was a placeholder for the virtual node. Well, now we can pass that in, and that message will be added in the update equation. But aside from that, this looks just like the code that was implemented before, where we're just running through the convolution layers, the batch layers, and then applying dropout if it's not the last. So that's the forward pass where we're sending messages from the virtual node to the all the other nodes. Finally, we need to update the embedding for the virtual node using messages from all the other nodes, because in this previous step, we just used messages from the virtual node to update the others, but we need to do it the other direction as well. And what we're going to do is very close to the graph pooling that we did before, where we took the average of all of the nodes for each of the graphs of each of the component graphs in our supergraph. And we're going to, instead of call mean nodes, we're going to call sum nodes. This is going to add up the embeddings for all of the nodes in each graph, which is the same thing as message passing with the sum operator. You add up all of the embeddings. And we're going to do that same thing here, but then we're going to have the self loop of adding in the current embedding as well. So this is a graph level output, because recall that our hvert graph has the 32 rows in it, where there's a copy of each of the virtual nodes for each of the graphs. So if we're doing message passing on each graph in the mini batch, we should expect to have essentially 32 iterations of message passing, and that's what this is going to do, right? It's going to sum all of the nodes in each of the 32 graphs, and the thing it's going to sum together is called h, which we store in here. And the output of this thing is going to be 32 rows, where each row represents the sum of all the nodes in each of the component graphs, which is all of the message passing without the self loop. So this is the self loop here, and we're going to call that virtual MP. So this represents the sum of all of the nodes, including the virtual node in each graph. And then we can pass this through our MLP with dropout. So that's that. We now have a new representation of hvert graph for the next layer, which we'll start using it right here. So we're using the same index, but this thing is going to be updated through each layer here, using this MLP and, of course, receiving the messages we just described. That was all pretty tricky, but hopefully it made sense to you. We go ahead and plug that in the exact same way as before. We see it actually does have improved performance. We're getting further out here to the right. Again, these numbers will look a little bit different from the one I uploaded because I ran this a second time, but the conclusion is the same. It's slightly better. I'm given some confidence that this is an actual improvement, because when we run this 10 times here or repeat it another 10 times and compare it to the 10 times on the leaderboard, it's consistently a higher mean, but it's by no means an enormous gain. But something that seems to work okay.